to re-watch that. So the next recording, I promised you to show you something. Okay, now I need to share a blank whiteboard again. Yes, on the non-adiabatic PFR reactor, I noticed that especially because we didn't go all the way back and did the whole derivation, some people are confused about whether we are making assumptions in the derivation or whether it is the truth. So if I consider this slice, so it's a non-moving fixed slice somewhere in my plug flow reactor. And if I do my energy balance over that slice. So let's just first do the mole balance. It's going to be, let's say I've got FA, so I've got FA at the inlet of that slice, so that is where V is equal to V minus FA when it comes out at V plus del V. So you should all remember this from your, well, maybe not remember it, that's a tall order. And then I've got this conversion that's in that slice, and that is equal to plus the rate in that slice times the delta V in that slice. Must be equal to 0. Then I divide by delta V, and I take the limit as that delta V goes to 0. And this then ends up with your equation where you have dFA dV. So this is just actually min that, okay? If I have that, it's negative of the delta, plus RA is equal to 0. Happiness. And then this is where our mole balance comes from, in case you forgot. Okay, so now when we do the same thing for our energy balance slice, okay. Non-adiabatic reactor. So the energy balance says it's whatever comes in at V, sum of everything that comes in at V minus sum of everything that leaves at V plus del V, out, everything out, this is everything in, at V plus del V. And then, now this is not equal to 0 because we've got heat flow, but still steady state. So let's leave it at steady state, that's why it's equal to 0. But now we have a Q term. And remember, Q is a path variable. I don't have Q at the inlet and Q at the outlet. That's not how we account for Q. So I will not Q at V and Q at V plus del V. That is just simply incorrect. Let me get a big red. That is wrong. I have Q that flows from del V. So I would rather say I have plus Q from del V. Okay? So now how do I calculate this Q? This Q is directly equal to a heat transfer coefficient, overall heat transfer coefficient, the area that is available in that small del V, in del V. So it's the heat transfer area available, and then in that slice is so small that we assume that whatever, regardless of whether the utility temperature along the total volume of my reactor, regardless of whether that is increasing or decreasing, or my temperature along the volume of my reactor does this. So it's not a constant, but in that little slice, there, if we just take that little slice, it's so small that we are going to assume that there it can be taken as a constant. So it's the driving force there, TU minus T. So we are not making the assumption when we derive this that we've got a constant utility temperature. This is the main misconception I noticed. So for CSTRs, we made that assumption that the TU is constant. Here, we're just assuming that in that small slice, it's so small that I can take the temperature of my slice at the inlet and the utility temperature as the inlet to be constant throughout that slice, or that del T is so small that it can be ignored. So now if I substitute this in there, and I take the limit, divide by delta V, so this will then be equal to minus delta H of my flowing streams divided by delta V, plus, and I'm going to have U, T, minus T, and then I'm going to have that small delta A, area available for heat transfer in delta V, divided by delta V. So there we go. I will tell you when you swap it. This is correct for the purpose of the fluid. Now, and that is equal to 0. So this delta U, delta I over delta V, that becomes that small little a, because for our tube, that is a constant. Because the area available per volume, we calculated that using the circumference times the delta Z. And the volume I can calculate as the cross-sectional area times the delta Z. So this ends up, please go and revise that as being equal to 4 over the diameter of my tube. That is what I substitute in there. And then, don't we need, yes, definitely. So for this test, we are going to assume this is constant. I am not going to expect you to change the TU like this. So I'm going on a sidetrack. So what I'm saying now is, regardless of whether this changes, this is going to be a value in that slice, right? And then if it's changing, what Sean is asking, my variables will be FA, FB, temperature, and TU. And I will need a differential equation for each of them to describe how they are changing. For us, for our purposes now, the TU dV is equal to 0 for now, right? So it stays constant, that slope stays constant. And now if I take this, so back to this, meantime, back at the range, and now back to the fields. If I take now the limit when delta V goes to 0, limit when delta V goes to 0, and I rearrange and I shuffle, it ends up being dH, sum of dH of my flowing streams, dV, is equal to U du minus t times A. Okay, because whether it's dA dV or delta A over delta V, it's going to give me the same answer. So I don't have any issues with the changing temperature and the changing U here. Why they are constant is because my slice is so small. It's the same as when you evaluate the rate expression in your mole balances. You assume that the FA, the change in FA is so small that you can actually use that inlet to calculate your concentrations, right? So this is like the rate of heat transfer is like a similar kind of equation to RA. That's the way we attack it. I was just seeing some people having misconceptions about the assumptions we are making. We are not making any assumptions when we derive this energy balance. When we model it currently, our assumption is that the TU stays constant so that its slope is 0 and it doesn't need to be a variable in that equation. So it's very easy actually to build in a differential equation for that, but we are going to practice that after the semester test. Questions? See if I've heard it. Yes, Sean was correct. And when you switch that, so let's just make sure that we've got the signs correct here. Okay, so if TU, let's do the reasonable person check. If TU is larger than the temperature inside my reactor, it means that TU must be positive. Heat must flow into my reactor and this stuff must heat up. Okay, and that is in fact true. If TU is larger than the temperature, this will give me a positive number. And let's just say I had no reaction in that slice. So this will only be equal to sum of Fi, Fi Cpi, dt dV. This is a Cp value. dt dV is equal to that Q. So I will see an increase in my temperature because that is going to be positive. If that TU is smaller than the temperature, this is going to give me a negative number. So Q will be negative and heat will flow from my slice. And that will therefore cause a decrease in the temperature, a negative slope of how temperature changes with volume. So no, from the perspective of our fluid in the reactor, we are not going to swap that. But when we are going to look at the fluid, the energy balances for our utility, there may be a swap depending on whether it's co-current or counter-current. But once again, watch this space, leave you in anticipation, waiting for the next episode in this riveting series. We will discuss that after semester test 1. Okay, more questions? Right, I think, okay, so I've got some questions. Let's just check. If you, not Lucas, I just want to ask, the reactor sequence, is this with coolers achieved? So definitely a different setup is better. So you are limited there. You are limited there. It's a suggestion and it's good for testing student purposes. But what we will explore, so now this CSTR thing there, that's for practicing, understanding what's happening with the rate. But what I would like to show you after the semester test is that it's actually when you have the ability to cool down while you're reacting. So maybe I utilize this nice warm temperature over here to drive my rate when the concentration of B is still relatively low. I use that high temperature. And then as the concentration of B becomes high, I suppress my reverse reaction by starting to cool down. So I can actually drive my reaction much further, or in fact, let's say to that 70% by cooling in a plug flow reactor and then actually choosing my path on this XT diagram. So that is what we will explore. But if you are limited and you were told that this is the setup that you are interested in, yeah, so yes, there is in fact a better option. Okay. Because we assume that the flow rate is high. Okay, that's now back onto the PFR reactors. Same range in temperature? No. Carrot? No. Okay, so let's just see what he says is if my reactor TU is a constant. TU is a constant. Right? TU is equal to a constant. However, the temperature of my fluid in the reactor, temperature of the stuff flowing there with volume, does this, let's say, if it's exothermic. So the difference between TU and T is not constant along the length of my reactor. So therefore my rate of heat transfer, Q, which is equal to U A TU minus T, and this is the blue one, that's constant. This is not constant. So the rate of heat transfer varies along the length of my reactor. I can actually, after I have run my simulation, and I have values for TU, and I have a range of values for T along the length, I can actually calculate the rate of heat transfer along the length of my reactor, and you will see that it is not a constant. How's that?
Thank you, ma'am. I actually meant if we assume that the utility temperature wasn't constant, would we assume that the utility temperature change was the same throughout the reactor at any slice?
The change in the utility temperature, no, because that will also depend on what is the difference between these two temperatures. So because the rate of heat transfer is not going to be constant, you may have a low rate and then it's go, or a high rate, then it's going to go lower and whatever. Because this rate is also, I will not get necessarily get a constant rate there for my utility temperature slope as well. Okay, cool. Right. Okay, anything else that bothers you? No, or you're not aware of stuff that bothers you yet, maybe. So in the semester test, please give me stuff to mark. Remember, sometimes it may be a consolation. If you think about the fact that not everyone is supposed to get full marks, that's very harsh, but not everybody is supposed to get full marks, but everyone is supposed to pass. So your answers may not be correct. Your answers that you put there in the little blocks may not be correct, but somewhere along the line you made a stupid mistake, like you had a variable error, and then you will get penalized for it because a part of the test is for the skills. But you may still earn most of your marks if you give me something to mark. You are serious about that. Don't worry. There are blocks where you have to write stuff in. And unless I give you, and where I must allocate a grade. And if I don't allocate a grade, your stuff will show as needs grading. I promise you, hand on my heart, I will not show you those zeros. Okay. My experience from employing these tests, most students get a 0. Most students get a 0. It's very rare for somebody to get full marks because this is now, I'm not giving you a pep talk here, but because it's so, to make no little sniggly mistakes, chances are very rare. And then, so that 0 doesn't mean anything. Also, there are questions that caters for you just need to get 50%. And there are questions that cater for you want a distinction. Right? And, not everyone necessarily can get a distinction. So please, if you think this is one of the questions, spend your time on the questions that you think you can actually achieve. And the marks, sometimes the marks are allocated in such a way that for a really difficult question, you feel, yes, like the marks are not, doesn't represent the degree of suffering that it took me to complete that question. So the marks don't look at the marks allocation to think which questions are the most difficult questions. Sometimes they are intentionally not weighted that significantly because I don't want everyone to fail. Okay, but so I think you are going to find all my questions in this semester test reasonable, very reasonable. If you've done all the touch, you are going to fly through it. Really, this is the pep talk part of the lecture. You are going to be good in the test. No owling, nothing that I want to catch you out. No, well, from my perspective, stay calm, do what you can, give me stuff to mark. All right, I'm going to stop the recording.